We're here at the Smart Lighting Conference 2017 in Hamburg, Germany with Bob Karlicek. Bob is the director of the Lighting-Enabled Systems and Applications Center at Rensselaer Polytechnic Institute in Troy, New York, where they do a lot of work looking into what I will, for the moment, call human-centric lighting. Not everybody likes that phrase, but it is lighting that is tuned to human beings to make them healthier and fit and just well-being beings. So, Bob, have I described that okay? I'm sure you can do a better job. What is human-centric lighting?
Well, we would argue in the U.S. that all lighting is human-centric.
Mm-hmm.
That lighting exists, artificial lighting exists, because people have a need to be well lit in all of their endeavors, because they spend a lot of their time indoors. So in many places, human-centric lighting has become an expression for learning how to use spectrum,
right,
to be able to take advantage of certain aspects of human physiology,
right,
to create better performance outcomes.
Okay.
So for example, the intrinsically photosensitive retinal ganglion cells,
right,
discovered in the 1990s,
by
being
Russell.
responsive to blue light, yes.
Right, Russell Foster and others at
And
Oxford.
others,
Yeah.
yes.
Mm-hmm.
Now have been studied in great detail to see that they in fact are not part of the visual system, but in fact detect light,
Right.
to be able to regulate human circadian rhythms.
Just to be, so these are photoreceptors in the eye that don't relate to vision, but relate to other aspects.
Yeah, and when you think about it, it's really fascinating, because we've known a lot about human physiology for a long time.
Right.
And to find out in the 1990s that there's yet another cell in the retina that plays a part in detection of light, but not for vision, to regulate human timing,
Right.
of circadian rhythm,
Right.
is really rather amazing.
Right, okay. And that responds well to blue light in the blue frequency. Is that correct?
Well, it turns out that when you take a look at the impact of wavelength on the peak response of these cells, you find out that it does respond in the blue to bluish green
Right.
range. But it's a rather broad response
Right.
function.
Right.
But it's in the blue.
So in that sense, the blue is virtuous. It stimulates and makes people more alert and ready to go. But blue has a bit of a villainous reputation at the same time. You hear a lot these days about blue light creating sleep problems by suppressing melatonin, the sleep-related hormone.
Yeah, I think that it's really an interesting study, and certainly our companion center at the University Lighting Research Center has done a lot of work on light coming from iPads or other electronic
Right.
devices,
Right.
Exposing people to a lot of spectral distributions that people, evolutionarily speaking, have not been exposed to. And so there's a question about whether or not this is good for people,
Right.
and whether or not it's good for their health and well-being. And so there's a lot of research going on in that space. This has been realized by a number of people, Apple, but more importantly, F.Lux, an application that you can purchase for your smart devices that reduces the amount of blue light you get from your smart devices
Okay.
at night.
Okay.
So people have kind of realized this, and so they've kind of developed applications that the aware user can have,
Right.
to be able to reduce blue light exposure at night.
Right.
Now, the exact meaning of blue light exposure at night is still being looked at. It's very, very clear that sufficiently intense blue light exposure at night can suppress melatonin formation.
Right.
And melatonin is a timekeeper that is responsible for regulating many of the other clocks within the human body. It's not really associated with sleep necessarily.
Right.
Evolutionarily, we've had melatonin peak in the dark at night, and that's when people sleep, because there wasn't a
Okay.
whole lot else to do.
Right.
But that's just a situational association. At the levels that the human body produces melatonin, it's not really at a level high enough to actually induce sleep. And sleep is a very complex process in and of its own right.
There are other factors involved. Yeah.
So the research community's become very interested in this because people have noticed in particular that shift workers who presumably have a disrupted circadian rhythm
Right.
tend to be more prone to certain kinds of diseases.
Right.
And as a result, some people think that light at night may be responsible for that.
Right.
But the correlations are not well established and require further research.
Okay. Okay. And this is what you're doing at.
No, we don't really do that kind of research.
Okay.
We work with people that are involved in that.
I see.
Because we're an engineering center, mostly what we do
Yeah.
is we look at the engineering control models for how
Yeah,
the
yeah.
body,
Yeah.
as a biochemical engine,
Right.
actually regulates melatonin and how melatonin control is related to light. So we look at light stimulus and determine whether or not there is a well-defined engineering control methodology that the body uses to regulate melatonin formation. We fact and find there is. It's a simple on-off switch.
Okay.
It's not a proportional control mechanism. A little bit of blue light is okay, but a lot of blue light is bad. There's a certain threshold clearly, but it's a simple, what engineers would call a bang-on control mechanism.
Right.
And so once we understand the control mechanism from an engineering standpoint,
Yeah.
we can now understand how to control lighting from an engineering standpoint
Okay, okay.
to interact appropriately with the human system.
Okay. So does this mean building gadgets, eyewear, apps? Is that the sort of thing you're doing?
It in part involves building lighting systems that are aware of how best to control light to manage a person's
So this
circadian
could be
phase.
lighting system, lights in the ceiling, lights in the walls, lights coming from specially designed glasses.
It could be any of that,
Yeah.
but mostly we focus on simple optimization algorithms. For example, if a person is jet lagged,
Right.
what is the best lighting recipe? Given how the body actually functions as a control system, what is the best lighting recipe to return circadian phase to its normal state as quickly as possible?
Right.
So it's a simple engineering problem, perhaps not so simple because we actually have to study human beings, and human beings are
They're not simple.
not simple to study.
Okay.
A lot of our early work was done on fruit flies, Drosophila, simply because when you're done with them, you can grind them up to find out what their chemistry is.
Right. Okay.
It's frowned upon with people.
I think you're right about that. Yeah.
But it turns out that we've learned a lot about those control mechanisms, and now we work with some very large lighting research programs like the light research program at Thomas Jefferson University.
Right.
Professor George Brainerd.
George Brainerd. Yeah.
And we share data and share ideas about exactly how to take our models
Yeah.
and fit them to actual human studies.
Right. I'm glad you mentioned George and Jefferson because he has worked on one of several scientists working on new human-centric lighting, circadian lighting. That's another phrase for it. Delivered up to the space station. Yeah.
So that's his program,
Yeah.
along with Stephen Lockley at Harvard
Yeah.
and others, where they've developed a novel controlled spectrum lighting system
Right.
to be able to, A, improve the overall lighting in the International Space Station, which needed to be replaced because it's gradually failing, and B, improve the performance and the sleep patterns of the astronauts that are there.
Because those astronauts experience sunrise and sunset every 90 minutes, if memory serves me well. That will wreak havoc on a circadian rhythm.
Well, they do, but only through a little portal in the
okay.
outside. But,
Okay.
But the lighting is on all the time.
Right.
Gravity and the absence of gravity
Right.
impacts sleep. The noise levels are rather high. There are many disruptors to sleep.
Right.
For that population, a very small population in the International Space Station. And so the question becomes, what role can lighting play to try to improve their overall level of performance and relaxation during sleep? So those systems are just now being installed and tested.
Okay, and I think they're starting out with a few, and then the idea is to add more.
I believe that's the idea.
Yeah.
Now, our center is not involved in that research,
Right.
but we're amazed to see the work that Professor Brainerd
Yeah.
and the team are doing to take a look at how
Right.
to use lighting in this very specialized environment.
Right.
And I'm sure they're going to learn a tremendous amount of information about
Yeah.
spectral management and human performance because, again, these astronauts are all extremely healthy
Yes, they
human
are. Yeah,
subjects.
yeah. They need their sleep.
Indeed.
So coming back to Earth, it doesn't have to be in a space station, obviously, and there are all sorts of implications for how this could be applied in schools, offices, healthcare facilities.
So indeed, yeah. So many people are looking at how, now that we have light-emitting diodes that allow us to more easily control spectrum on demand,
right,
to be able to take a look at how we can use this new spectral management to improve human performance in a wide variety of applications. There are many research programs all throughout the world
right,
working to demonstrate the benefits of using spectrally tunable solid-state lighting systems to impact human performance. And so it's going to be very interesting to see where this research goes.
right.
It's going to take time to get there because, you know, again, working with people is complicated. In order to convince someone, a building operator, for example, or a healthcare facility manager, to install solid-state lighting, especially with advanced controls
right,
to do spectral control, there's a certain budget associated with
sure,
that. And until there's a clear value proposition
right,
without any risk
yeah,
of adverse impact, it's going to be difficult to make that sale.
right,
And so part of the research that needs to be done, in the opinion of myself and many other researchers in this space, is to really take a look at establishing an evidence-based, ironclad research foundation
right,
for the impact of spectrum on human well-being and performance.
right,
We have a lot of research programs that show promise,
sure,
that there's real impact there.
yeah,
Many people are very excited about it.
yeah,
But if I were to go to a hospital manager and tell them that they need to install this lighting because their patients will recover more quickly, they say, show me the evidence, and all I
right,
have are a few studies here and there.
right, yeah. So there are some companies out there saying that in some hospitals where the nurses and the caregivers are reporting anecdotally an improvement in the patients. And I think what you're talking about is more scientific evidence.
Well, not only scientific evidence, but you know, this whole issue of variable spectrum is relatively recent. So if you take a look at some of the people that do lighting research on human beings,
right,
they just take a look at correlated color temperature and intensity.
right,
But really, you need to take a look at the entire spectral power distribution.
right,
You need to measure it in various locations and directions.
right.
Because, you know, most of our time is not spent staring directly at the lights.
No. And to that end, a lot of the time, the light, you need to measure how much light is actually entering the eye.
It's the ideal way to figure out what your light dose is. But it even gets more complicated than that because, you know, the distribution of these intrinsically photosensitive retinal ganglion cells
right,
are not uniformly distributed on the retina.
right,
So it's the angle of arrival to the eye, and certainly the spectral power distribution plays a role. So where I'm looking, where the light is coming from,
yeah,
all these play a role to my daily light dose integral that factors into
right,
the amount of light I get.
Lisa, your group is building eyewear to help measure the light.
Well, we would like to build a research tool that's
yeah,
a little bit more sophisticated than some of the research tools
right,
that exist right now have been. You know, until very recently, it was very hard to put a spectrometer on somebody's head
okay,
and measure the spectrally resolved light dose because
right,
they've been big, expensive, and bulky.
okay,
So what people have done is traded off precision in spectral measurement for very simple photodiodes with color sensors. But fortunately for the entire research community,
yeah,
new technologies are evolving right now. So for example, some very, very compact spectrometer sensors about the size of a pea.
right,
We're experimenting with ones from a company in Korea called NanoLambda
wow,
that are very lightweight, have very, very good spectral resolution capability for the kind of studies we want to do, and can be easily head-worn,
okay,
so long as you can find somebody that's willing to wear the apparatus for studies.
okay,
And so the idea would be, with a given population, and students are ideal for this, so long as you can offer to pay their cell phone bill for a week
right,
or more while they wear the apparatus, to figure out what kind of light they've been exposed to, what their light dose has been,
yeah,
where they've experienced it, what kind of lighting they were in front of, because if we can measure spectrum, we can tell if they're in front of incandescent LED
Right.
or fluorescent lighting.
Right.
And so we can do
Wow.
all these things now, and so we're looking to complete the full development of this unit. It's being done with students who are really very clever, but unfortunately they have to go to classes and take exams. So
Yeah.
it's a little slower than it would be in industry.
Right, right.
But we're doing this now, and we should be able to start experiments hopefully this fall.
Right, right. There's a similar set of glasses from the LRC at
Yes.
Rensselaer. Yeah.
Yeah, we helped fund some of the development
Right.
work or some of the commercialization work
Yeah.
for what was called the daysimeter.
Right.
And they still do work with a similar kind of system that I believe is worn around the neck.
Okay. Okay.
But again, we're looking for something that can possibly do a better job of spectrally resolved
Right.
ocular light dose.
Right. Okay. Advancing it. Yes. Well, I mean, wouldn't it then be great if you could prove, say, in the office workplace, that spectrally tuned lighting improves productivity?
Indeed. So, you know, and there we want to be able to work on a wide variety of things
Right.
that we also do at the center. So, for example, we control the spectrum of light, that's fine. We also have developed interesting sensing technologies that can figure out where people are and what they're doing just by processing the data in reflected light. And what's really unique about our approach is that we actually make the lighting an integral part of the sensing system.
Yeah.
Because by controlling the spectral power distribution, digitizing that spectral power distribution, and then even measuring how long photons take to get from point A to point B, we can complete a full three-dimensional map of the space without using a camera. So privacy is preserved, and we can essentially figure out where people are and what they are doing, and through estimating their activities, estimate what kind of lighting profiles are appropriate for that activity. We can also use this data to report information to building management systems,
Right.
for regulating space utilization, for HVAC control.
Right.
You know, the data is something that everybody wants out of lighting systems nowadays for all these value-added services.
Right.
What's unique about our approach is that we actually make the lighting system an integral part of the sensing program by making special lights to do special things
Right.
that make the light field sensing easier.
Right. Right.
And so it's a very exciting place to be.
Okay. And this is a high-tech version of what's been going on for millions of years. Humans living under the sun, getting biologically conditioned by the rising and the setting of the sun and its different spectral content by the time sunlight reaches the Earth. So
Yeah.
this takes that age-old concept and puts a nice modern digital lighting.
Yeah, but in some sense we're
approach.
moving back to the old age, or
Yeah.
the early times,
Yeah.
because, you know, human beings in a natural environment are not exposed to static light. Static light is an invention
Yeah.
of indoor lighting.
Yeah. Yeah.
But now that we have LEDs and we can change the lighting dynamically,
Yeah.
including various kinds of settings that
Yeah.
involve changes in spectral power distribution, intensity, on a wide variety of time scales, all
Yeah.
because solid-state lighting is digital.
Yeah.
We may actually be able to create much more lighting, much more natural lighting environments indoors
Right. Right.
without having to have daylight.
Very promising, very fascinating. Good luck with it all.
Thank you very much, Mark.
Okay, Bob Karlicek from Rensselaer's Lighting Systems and
Lighting-enabled
systems and applications.
It's a
Research group.
it's a mouthful.
Yeah, LISA,
LISA.
LESA.
That's why we have the acronym.
Right. Okay, Bob. Thank you very much.
Thank you, Mark.